This is video number 3 for. So let's begin by looking at what we call the Cauchy convergence criterion. This one says that a sequence xn of real numbers converges if and only if is a Cauchy sequence. A sequence xn of real numbers converges if and only if is a Cauchy sequence. That is, if a sequence of real numbers converges, then it must be a Cauchy sequence. And if a sequence of real numbers is a Cauchy sequence, then it must also converge. So we have already seen the fact that if xn converges, then it's a Cauchy sequence, and also that if xn is a Cauchy sequence, then it's bounded. So now let's just prove look at the converse, the reverse, that if xn is a Cauchy sequence, then it converges. So let's assume that xn is a Cauchy sequence, right? We've seen before that if xn is a Cauchy sequence, then it's bounded, okay? And then the Bolzano-Weierstrass theorem tells us that if a sequence is bounded, then it has a convergent subsequence. Now, since every Cauchy sequence is bounded, then the Bolzano-Weierstrass theorem ensures the existence of a subsequence x and k of our Cauchy sequence xn, okay, which converges. And let's assume that this subsequence converges to a limit x star, okay. Now, we want to show that our original Cauchy sequence must also converge the same limit, which is x star. All right. So since let epsilon bigger than 0 be given, now since xn is a Cauchy sequence, then we can find a natural number capital N epsilon such that if small n and small m are bigger than that capital N epsilon, then the distance between xn and xm is less than epsilon over 2. Here we are simply using the fact that xn is a Cauchy sequence. All right. Now, since our subsequence converges to x star, then there is a natural number epsilon. I will call it m epsilon, such that if nk, right, this nk here, if nk is bigger or equal to m epsilon, then the distance between x and k and x star is less than epsilon over 2. Here we are simply using the fact that the subsequence x and k converges to x star. Now let capital H be the maximum of n epsilon and m epsilon, and then fix nk. Let nk be fixed. Fix it such that it is either equal to h or bigger than h. All right. Then, if you do that, then the distance between xn and x star can be written as this, right? You simply introduce minus x and k plus x and k, where nk is fixed here. You can actually fix it to be h, so this will be xh. All right, let's keep it as nk. So you simply add x and k minus x and k, and then you add x and k. Right? Then you use a triangle inequality. Together, this is less or equal to the distance between xn and nk, and the distance between x and k and x star. But we know this is less than epsilon over 2. We saw from the previous page, because xn is a Cauchy sequence, right? And this is also less than epsilon over 2, okay? Because xn converges to x star. You can see that one here, right? So long as both nk and n are bigger than the capital H, and so this is equal to epsilon. So that tells you that xn converges to x star, right? Okay. Now let's consider the following example. Let xn be the sequence defined by setting x1 to be 1, x2 to be 2, and xn to be 1 over 2 times xn minus 2 plus xn minus 1 for n bigger or equal to 2. Now we show that the sequence xn is Cauchy and therefore converges. So we are going to write down a few terms of the sequence, right? Okay. If you write down a few terms of this sequence, then you can see that it's not monotone, and therefore the monotone convergence theorem will not be of any help here. So we are going to show that xn is a Cauchy sequence, and then we will conclude that it converges. Now, for n bigger or equal to 2, we see that xn minus xn plus 1 can be written as this. All right? The distance between xn and xn plus 1 can be written as, I've kept the xn here, but this is a xn plus 1. All right? So just expand this one and simplify, and then you see that this can be written as that. Then you see simply interchange xn minus 1 and xn to get this. All right? Because these two are the same, doesn't matter the order in which you write them, since we are looking at the magnitude. All right? Now keep this xn minus 1 here, and then this is just an expression for xn from the formula given on the previous page. Again, simplify this, okay, and do the subtraction, and you see that that can be written as this. All right? With 1 over 2 to the power 2. So again, this expression here, right? This expression here is simply xn minus 1. Again, simplify, do the simplification here, and you see that it can be written as this. Then you continue the process up to when you get to xn minus 1, and the term that you will have here will be 2 to the power n minus 1. So the conclusion is that the distance between xn and xn plus 1 is simply equal to 1 over 2 to the power n minus 1. The distance between xn and xn plus 1 is simply 1 over 2 to the power n minus 1, and this is true for all n. All right. Now, we want to show that xn is a Cauchy sequence, okay? So assume that m is bigger than n, right? Then, if m is bigger than n, then you have that the distance between xn and xm can be written as, this is your xn, and this is minus xm, right? So you simply introduce minus xn plus 1 plus xn plus 1 minus xn plus 2 plus xn plus 2 up to minus xm minus 1 plus xm minus 1, right? Use a triangle inequality to say that this is less or equal to the distance between xn and xn plus 1 plus the distance between xn plus 1 and xn plus 2, and so on, up the distance between xm minus 1 and xm. And then using the previous, what we saw on the previous slide, we see that this one, right, is less than 1 over 2 to the power n minus 1, right? And because we saw that the distance between xn and xn plus 1, right, is equal to 1 over 2 to the power n minus 1, right? So apply the same formula to this one to see that this one is equal to 1 over 2 to the power n. So we saw in the previous slide that the distance between xn and xn plus 1 is 1 over 2 to the power n. So use the same formula to see that the distance between xn plus 1 and xn plus 2 is equal to 1 over 2n. And similarly, that the distance between xn plus 2 and xn plus 3 is 1 over 2 to the power n plus 1. And you continue up to when you end up with the distance between xn m minus 1 minus xm is 1 over 2 to the power m minus 2. Okay? So you simply factor out 1 over 2 to the power n, and you have this sum here, okay, which we write in summation notation as that, right? And this is less than, okay, we take the sum up to infinity, right? So this one is less than that one. We have kept this one the same here. Okay. Now this is a convergent geometric series, okay, and converges to this number here. Okay. So you simplify this expression to get that one. Okay. So what we are saying is that if m is bigger than n, then the distance between xn and xm is less than 1 over 2 to the power n minus 2. So if m and n are natural numbers with m bigger than n, so we have this expression here. That's what I was saying above. The distance between xn and xm is less than 1 over 2 to the power n minus 1. So given epsilon bigger than 0, you simply choose a natural number n such that 1 over 2 to the power n is less than epsilon over 4. This is possible by the Archimedean property. If you do that, then you end up with the distance between xn and xm, all right? You end up with the fact that if small m and small n are bigger than capital N, all right, then the distance between xn and xm will be less than 1 over 2 to the power n minus 2, and that is simply 4 over 2 to the power n, which is less than epsilon, right? And so the conclusion is that xn is a Cauchy sequence.